In this next segment, we are going to, let me share screen. We're going to be talking about vapor pressure and the relationship of vapor pressure to the heat of vaporization that we just talked about in the previous segment. So let's talk a little about the process of evaporation. So in evaporation, a liquid in a closed container evaporates. The liquid leaves the molecules leave the liquid state and go into the vapor phase until the rate of condensation, the rate of molecules going from the gas back into the liquid is equal. It's called until it reaches equilibrium. A couple important terms here. The vapor pressure is the pressure at which a liquid is in equilibrium with its vapor at a given temperature. It's not necessarily the pressure of all the gases above that liquid, but it's the pressure of the gas corresponding to molecules of that liquid. The boiling point is the temperature at which a liquid is in equilibrium with its vapor at a given P. So we can take a given pressure and find the temperature that's its boiling point, or we can take a given temperature and then go up and down the pressures until we find the vapor pressure. And again, what you get in this process is a dynamic equilibrium. You get, at the beginning, it's all liquid. And so the rate of evaporation will be constant. It'll be proportional to the amount of area there is, because you can only have evaporation off of the surface. It'll also be proportional to the temperature. We'll get those there soon. So liquid will come off the surface into the gas phase. And at the beginning, the rate of, you'll get evaporation, you'll have no condensation because there's no vapor. But over time, you get more and more vapor that goes into the air of the bottle, and it will start condensing back, right? Because you can follow that process as well. So it'll condense back, and that process will keep on going. There'll be more and more vapor until you reach the state that the rate of condensation is the same as the rate of evaporation. Now, obviously, the temperature is going to change that those rates, but whatever the temperature is, that'll just change the ratio of liquid to vapor that you have. You'll always reach this point where they're in equilibrium. And so what's the process by which molecules can escape from a liquid? When I first learned this, I was really confused because I thought that, well, you had a heat of vaporization. Didn't you just need to get you heated the entire system up and then all of the liquids vaporized at once? But that's not quite how it happens, because remember that the molecules have a distribution of kinetic energies. Some of them are moving fast and some of them are moving slow. And so once molecules get enough kinetic energy just from jiggling around and bumping into other molecules, once they have enough energy to sort of get out of the intermolecular interactions and they're at the surface, then they'll escape, they'll fly off. Once they've gotten out of those interactions, they'll fly away. And once they're flying away, they'll keep on flying until they eventually, maybe bounce back down. And so that's what you're looking at. Evaporation occurs when that small fraction of molecules has enough thermal energy to escape from the interactions. So it makes a lot more sense then why at higher temperature you have a higher rate of vaporization and you have a higher vapor pressure, because there's a lot more molecules as the temperature goes up that has sufficient energy to break out of the intermolecular interactions. And it turns out that just a small change, so essentially that the kinetic energy to escape is the heat of vaporization for that single molecule. It doesn't all evaporate at once. It evaporates as soon as some fraction of it gets up enough energy. And this is you can see the cooling process as well. As it evaporates, then it takes away some of the kinetic energy of the system, and the system is left cooler than it was before. Now, one interesting thing is if you look at the tails here, a small change in the temperature, which is the average kinetic energy of all the molecules, actually results in a significant increase in the fraction escaping. Here, we've only shifted the temperature by a little bit, but you can see if you go to the areas under these curves, you've maybe like tripled the fraction of the molecules that have enough energy to escape. And so you can show, we won't do it here, but if you look at these distributions, the fraction escaping is some constant that we won't worry about what its value is, but the fraction escaping is proportional to exponential minus delta HVAP over RT. So whatever the heat of vaporization is dividing by RT, As the temperature gets higher, then the fraction escaping gets larger, and it goes up exponentially. So small change in temperature results in a large change in what can escape. So I'm not justifying the fact that it's exactly exponential, that we're dividing by RT, but I am justifying the fact that a small change in temperature results in an exponentially larger amount coming out. Okay, so we have evaporation for the liquid. Let's think a little bit about this exponential relationship between the fraction coming out and what's happening. So you have an exponential increase in the amount that's coming out. The rate goes up exponentially, and then that keeps going, and the rate of condensation compensates. And so what you get is that the partial pressure as well is exponentially related to the vapor pressure of the liquid. The vapor of that molecule above the liquid is exponentially related as well. So and so when we talk about the relative humidity, what we're talking about the percentage of the vapor pressure that's actually in the air. That's what we talk about. We say, oh, it's a 80% humidity out. That means 80% of the the current amount of water in the air is 80% of the vapor pressure. So it's not yet in equilibrium. If you were near a large body of water and you were just sitting there with like a container about you, you would keep rising up until it did reach the vapor pressure. But obviously you've got wind blowing everything away, and you don't quite have all of that. And so that's why the heat and the humidity have such a big interplay, because at freezing, the vapor pressure is way lower than it is at 100 degrees C. So there's, even if you're at 100% humidity at freezing temperatures, there's just not that much water in the air compared to at 100 degrees C. So this is why cold air is drier. And everyone talks about cold air being dry. It's because it can hold much less water, because the water doesn't have enough kinetic energy to escape from liquid puddles of water and go into the air. Okay, so as I said, the vapor pressure is also proportional, a different constant proportionality to the fraction escaping. But it's when you look at those things, you find that the vapor pressure is proportional to exponential minus delta H vap over RT. And so this is a sort of curve you get as the temperature changes.